Hello and welcome to Edu Sathi's lecture on syllogism. What is syllogism? Syllogism is also called deductive reasoning. It is a kind of logical argument that applies deductive reasoning to arrive at a conclusion based on two or more propositions. Propositions are also called premises that are asserted or assumed to be true. For example, I have one statement: all men are mortal. Then I have a second statement: Socrates is a man. Now, therefore, I can say that Socrates is mortal. This is what is called syllogism. Let's move on to some basic definition of what a premise is and what a proposition is. Now, you don't need to remember these definitions, but it is just to form a good foundation that you should know. Now, a premise consists of four parts. The first part is determiners or quantifiers. These are things like all, no, some, etc. Like in the previous example, we took all men are mortal. So here, all is a quantifier. It tells how many men. Similarly, I can have some men are mortal or no men are mortal. So these are called determiners. What is a subject and a predicate? It is a set of things or people. For example, I have all pens are black. Now, pens is the subject here, and predicate tells me something about the pens. So, here it tells me that all pens are black in color. Similarly, if I have another example, cars are automobiles. So, cars is a subject here, and automobiles, it tells me about cars, that car is a type of an automobile. So, automobiles is the predicate. Now, verb are is, are, may. Like here I have are, all men are mortal. So these are the verbs. So the four things are: we have a quantifier, we have a subject, we have a predicate, and we have a verb. Let's move to the next slide. Classification of propositions. The first type is the categorical proposition. Now this is the most important one, and this is the only one we will discuss in detail. In this proposition, there exists a relation between the subject and the predicate without any condition. For example, all cups are plates. No boy is girl. There is no condition. Then we have hypothetical propositions. In this proposition, the relationship between the subject and predicate is conditional. For example, if it rains, then boys will play. If he comes, I will not go. So there is a condition. If he comes, I will not go. If he does not come, I will go. So there is a condition. Whereas here, I have no condition. And the third type is disjunctive proposition. In this proposition, the assertion is of alteration. For example, either he is honest or he is loyal. So either of the two. So there is an alteration. Either he is educated or he is illiterate. So again, I have an or condition or an alteration. Let's discuss categorical propositions. Now, either we'll have an affirmative or a negative proposition. Affirmative means a sure yes, and negative means a sure no. Now, what is universal? Universal is something which applies to everybody. So I'll have the quantifier as all here. All P are Q. This is affirmative. And no P is Q. It is a negative, but no means that not a single P is Q. So that is why it is universal. It applies to all P. And here also it applies to all P. Particular cases when the quantifier is some, or let's say few. So I have some P R Q. This is a positive statement. So I have this affirmative particular statement, and this is some P are not Q. So this is particular because there is some, and because there is a not here, it's a negative. So it's a particular negative. Let's discuss the first type, which is universal affirmative. So I have this one here, universal and affirmative. All P are Q. It means, let's say I say all girls are good. So here P is girls and Q is good. It means that if P is a subset, like let's say I have a set A, B, C, D, and then Q is another set, A, B, C, D, E, F. Then the P will be a subset of Q. All P will lie within Q. So when I draw a diagram, I have this P, and this entire P will lie inside another bigger circle, which is Q. Or what I can have is P is ABCD and Q is also ABCD. So P and Q are basically the same circle. In this case also, since P and Q are the same circle, so all P become Q. In other words, if you want to think of it as in a simple way, you can think that, see, everything which lies in this circle is for P, and everything which lies in this bigger circle is of Q. And since this smaller circle is in this bigger circle, so all P belong to Q. Let's move on to the second type. The second type is universal negative. So we are in this quadrant here. I have a universal and a negative one. No P is Q. Now it means that if P is ABCD, then Q is EFGH. There is no common element here. So if I have this as a circle for P, I will have another circle for Q, as I have shown here. So there is no overlapping. Q has no business with P and P has no business with Q. So no P is Q also means no Q is P. Let's move at the third kind. Now we have particular affirmative. So particular affirmative is this. This is the third case. Particular means I have some. So some P are Q. Now what does this mean is at least one element of P is Q. At least one. So if I have A, B, C and D as P and Q as C, D, E and F. So I see that C and D are common here. So at least one P is Q. If I look here, then I have A and B here. If I look here, again I have AB and AB, and if I look here, all these four elements are same. So by this set, it is clear that there should be at least one element here in P which should also occur in Q. Now let's look at it diagrammatically. Now this is P and this is Q. As you see, this circle here, let me change the ink color. Now this part here of P also belongs to Q. So I can say that some P are Q. So this is correct. Here all the P belongs to Q in this bigger circle. So here also I can say that some P are Q. So some is a subset of all. I know here that I have shown that all P are Q, but this is a limiting case and this is also true. Because if all P are Q, it also means that some P are Q. Similarly, I draw the opposite circle. Now here, this Q part, the P is also there here. So here also some P are Q is valid. Now P is the bigger set here and Q is the smaller set. If I look at these sets here, P has 4 elements and Q has only 2 elements. But still, there are some P which exist in Q. So this is also a correct formation. And then we have, if P is equal to Q, we have the same circles. And here, since all elements of P are there in elements of Q, we can also say that some elements of P occur in Q. So this is also a correct one. But generally, when we solve questions and we have a statement like this, some P are Q, we will draw this diagram. All these other 3 diagrams are just to show you the possibilities. That what other possibilities are there. Let's move on to the last type, which is particular negative. So I am somewhere here. Some P are not Q. Again, look here, I have A, B, C and D. C and D occur here, but there are some P which is A and B which do not occur in Q. Similarly here, I have C and D which do not occur in Q. So some P do not occur in Q. And here all these elements of P do not occur in Q. So if everything in P does not occur in Q, I can also say that some of P do not occur in Q. So diagrammatically, now these are the elements of P which do not occur in Q here. So this is a correct diagram. In this diagram, I have this parts here which are outside the circle of Q, which are elements of P but not of Q. So this satisfies this condition, some P are not Q, so this is also correct. And then I have in P entirely different from Q. So here no element of P is same as that of Q. So I can here again say that at least one P is not Q. So this is also correct. But again, generally we will use this diagram here, and the other two are just possibilities. So when some P are not Q, it means that at least one P is not Q. At least one. It may be that all P are not Q. This is also a case. All P are not Q, as in this case here. But at least one P is not Q. These four things will form the basis of syllogism. If you've not understood them, just rewind the video and go through them again. Some typical examples: A-type propositions. Now you don't need to remember these name of the propositions. You just need to understand that there are four different types, and I'll explain you what is the difference. All positive propositions beginning with every, each, any are called A-type propositions. So we have two conditions here. The first thing, that they should be positive, and second thing, they should be beginning with words like every, each, any, etc. So if I have a statement like every cat is a dog, it means that all cats are dogs. This is the conclusion I will draw. This is where the use of these words become very important. Anyone can pass this exam. It means that all students can pass this exam. So this is again the conclusion here. Each of the boys of class 8 has failed. It means all the boys of class 8 have failed. So these are the A-type propositions, wherein I have a positive proposition and a word like every, each, any, which actually represent nothing but all. Let's move on to the second type, the E-type propositions. All negative propositions, so the first thing is negative, beginning with none, not a single, no one, are called E-type propositions. For example, none of the students could answer the question. It means that no student answered the question. Not a single person can climb the Everest. It means that nobody can climb the Everest. So it is basically again this none, not single, no one represents all, but in a negative sense, such that none of them, not even one of this, all can do this thing. That is why it's a negative proposition, and we have this E-type propositions. Again, you don't need to remember the names. You just need to remember that if I have a statement like this, this is the conclusion. If I have a statement like this, then this is the conclusion. Let's move to the third type, I-type propositions. All positive propositions, the first thing, beginning with most, a few, generally, almost, frequently, often, are I-type propositions. For example, almost all vegetables have been sold. So what is the conclusion? That some vegetables have been sold. If you remember A-type propositions, we had here each or every vegetable have been sold. It means that all vegetables have been sold. If it was a A-type proposition, then we would have an each here. But since I have almost, it means that I can only say that some vegetables have been sold. I cannot say that all vegetables have been sold. Most of the students will qualify for the examination. What is the conclusion? I can only say that some students will qualify. I cannot say that all students will qualify. All would have been here if I mentioned here instead of most there was an each. Each of the students will qualify the examination, which then becomes a A-type proposition. Then the third one, boys are frequently physically weak. So it means that some boys are physically weak, not all of them. Let's move on to the fourth type, the O-type propositions. All negative propositions beginning with all, any, every, and each are O-type propositions. For example, all innocents are not guilty. What is the conclusion that I can draw? Some innocents are not guilty. All that glitters is not gold. It means that some glittering objects are not gold. Now mind you, if you are thinking that can you draw a conclusion like some glittering objects are gold, this question might be coming in your mind. you cannot draw this conclusion. Why not? We'll discuss in the next slide. Everyone is not present, it means some are not present. I cannot say that some are present. I cannot say this. I can only say that some are not present. All innocents are not guilty, some innocents are not guilty. I cannot say that some innocents are guilty. Why is this so? We'll discuss in the slides to come. So let's look at some of the important rules which we need to remember. Never draw a negative conclusion from a positive statement. This is rule number 1. For example, I have a statement, some boys are girls. Can we say that some boys are not girls? The answer is a no. Why? Because this is a positive statement, some boys are girls, and this is a negative conclusion because of this not. So we cannot draw a negative conclusion from a positive statement. Now why can't we do so? If you remember the particular affirmative statements, these are the diagrams which we drew there. Now here it was some P are Q, and here I have some boys are girls. So I have P is equal to boys and Q is equal to girls. Now let's look why this conclusion is false diagrammatically. So if P is boys, I can write boys here and girls here. If I look at this diagram, I can easily say that some boys are not girls because I have this set of boys who are not girls. So for this first case here, the conclusion is correct. Let's look at the second case. Now P are the boys here and Q are the girls. Now in this case, as you see, all the boys are girls because the P is the circle, or the boys circle is inside the bigger circle here. So here this conclusion, some boys are not girls, becomes incorrect. So even if in one of these 4 cases this conclusion becomes incorrect, we cannot say that this is a valid conclusion, because as I said, all these cases are equally likely, but we generally take this case. But all these are possibilities. Even if you take in this last case, here we have boys equal to girls. So all boys are girls. Again, we cannot say that some boys are not girls. So here also this conclusion goes incorrect. Let's move on to the second important rule. Never draw a positive conclusion from a negative statement. For example, some chocolates are not crunchy. Can we say that some chocolates are crunchy? Again, the answer is no, because this is a negative statement because of the not here, and this is a positive conclusion that we are drawing. Now why is it so? We'll see diagrammatically again. If you remember the particular negative statements, this is a particular negative statement. These are the 3 diagrams which we drew. So some P are not Q. So P here becomes chocolates and Q here becomes crunchy. So from this first diagram, I have these chocolates which are not crunchy, and also this set of chocolates which are on the intersection of P and Q which are crunchy. So I can draw this conclusion from this first diagram that yes, some chocolates are crunchy. Let's move on to this second case here. Again, I have P chocolates and I have Q which is crunchy. So these chocolates which are on the outside of Q are not crunchy, and these chocolates inside of the Q are crunchy. So here also this conclusion holds good that some chocolates are crunchy. Let's move on to this third diagram. If this conclusion also fares good here in this third diagram, then it's a valid conclusion, but we'll see it will not. So I have crunchy here and chocolates here. Now this also means that some chocolates are not crunchy because all chocolates here are not crunchy, but here there is no overlapping between the P and the Q circle, between the chocolates and crunchy. So here I cannot say that some chocolates are crunchy. So even if the conclusion fails one of the tests or one of the possibilities, it is not a valid conclusion. So therefore, what we remember is never draw a positive conclusion from a negative statement. In the examination, just remember these rules. You don't need to form these 3 diagrams and then recheck. It is just for your understanding. Let's move on to the third rule. The difference between all and only. If there's a statement like all P are Q, it means that everything in P is Q. So as you see here, Q is the outer circle and P is the inner circle. So if I make a point here in P, it is also a point in Q. And this holds true for any point in P. So this is the diagram for all P are Q. Only P are Q, it's the entire reverse diagram. It means that Q is inside and P is outside. It means that, for example, I have another circle, let's say A here, or I have another circle B here. Now there will be no intersection between Q and B and Q and A. Why? Because only P can be Q. So in this circle only P can be Q. So that is why Q is the smaller circle here and P is the bigger circle. The fourth rule, some, few, little are all synonyms and subset of all. For example, if I say some priests do not tell a lie, does it mean that some priests tell a lie? No. Why no? Because this is a negative statement and this is a positive conclusion. Negative in the sense, don't go by qualities, but I have a not word here and I do not have a not word here. So some priests do not tell a lie. The diagram may also be like this. These are priests and this is line. So it might be that all priests do not tell a lie. This is the second rule which we did. Now, few priests do not tell a lie. What I have done is I have just replaced some with few here. It does not make a difference. Again, the answer is no. If you have problem in understanding this, go back to the second rule and you will understand. Now, what all we have done till now, if all P are Q, it means P is the inner circle and Q is the outer circle. If all Q are P, it is the entire opposite, that Q is the inner circle and P is the outer circle. Here every Q, if I make any point in Q, it is also a point in P, and here if I make any point in P, it also automatically becomes a point in Q. If it is mentioned that all P are Q and all Q are P and I add both, it means that P is equal to Q. No P is Q is same as no Q is P. This is the inference you can draw from each other. If there is no point in P which is also a point in Q, then similarly there is no point in Q which is also a point in P. Some P are Q. As I mentioned earlier, this is the diagram which we will generally use. So some P are Q, it means that this small amount of P also lies in Q, and some Q are P, it means that here some amount of Q also lie in P. Now this is a particular case for the positive one. The last case, some Q are not P. Again, I have this set, some Q which are not P and some P are not Q. Again, I have these P which are not Q. Let's move to the next slide. Now, what is the general format of the question? You'll be given 2-3 statements and then you'll be given a few conclusions. So you have some statements like 1, 2, 3 statements like some P are Q, some Q are P, something like this, and then you'll have conclusions. So you have conclusions which you will have to draw from these statements. Then you'll have answer options like A if only conclusion 1 follows, only conclusion 2 follows, both 1 and 2 follow, either conclusion 1 follows or 2 follows, and neither of them follows. We'll do some practice questions and then it will be clear. Question 1. Some spoons are small. So some spoons are small. I take this one circle as small and this another circle as spoon. All small are big. So the big will be a bigger circle because it has to take care of all smalls. So this is the circle big. The conclusions, all bigs are small. No, because I have some bigs here which are not small. So this is an incorrect conclusion. All small are spoons. This is also incorrect because I have some smalls which are not spoons. So here neither of the two conclusions follow. If you are wondering, you can also draw the circle for big like this, like you have a small here and then you can have a spoon. This is also correct diagram, because if this is spoon and this one here is small and this circle is big, even then because it just touches the boundary of small, it the big takes care of all small, so all small are big also is taken care of in this. Let's try another question. Some papers are needles. It means I have papers here and I have needles here. Some papers are needles. All needles are sharp. So I'll have something like this. I have a sharp circle which is circumscribing or a bigger concentric circle to needles. Now what are the conclusions? All papers are sharp. This is incorrect because I have a few papers here which are not sharp. All needles are papers. This is again incorrect because I have a few needles here which are sharp but not paper. So again my correct answer is neither of the two follow. All businessmen are hardworking. So I have all businessmen here. I'll write BUSI here for businessmen. All businessmen are hardworking. It means that hardworking is the outer circle. And then I have no hardworking is superstitious. So we draw a line here to show that there is no relationship between hardworking and this is the circle for superstitious. Now can we say the first conclusion, no businessmen are superstitious? This is correct because businessmen lies inside hardworking and there is no common platform between hardworking and superstitious. As you can see, businessmen and superstitious do not overlap here. So this is a correct conclusion. Then we have the second conclusion, all superstitious are not businessmen. This is also correct because we see that there is no again overlap between superstitious and businessmen. If you remember, no P is Q is also equal to no Q is P. So no businessmen are superstitious also means that all superstitious are not businessmen. Also diagrammatically there cannot be an overlap between businessman and superstitious. So here both the conclusions follow. So the next question here is all educated people read newspapers. So if I have an educated people circle here, then I'll have a bigger circle for reading newspapers. Then I have Raj is not a newspaper. So I draw this line to show that there is no connection between Raj and a newspaper. Now I deliberately mentioned here Raj is not a newspaper because in the exam you generally get confused that Raj is the name of a person. How can he be a newspaper? And then you start thinking that the question in the exam is incorrect. The first thing I told you was never to assume things. Raj can be anybody here. Okay, so you not assume anything. You'll only draw these circles and see if the conclusions follow. So the first conclusion is Raj is not an educated person. Educated person is within reading newspapers and Raj is outside. So Raj is not an educated person. This is a correct conclusion. No newspaper are educated people. No newspaper educated. This is incorrect because every newspaper which is inside this is also an educated person. So the second statement here is incorrect because there are some newspapers which lie within this smaller circle which are educated people. So here only conclusion 1 follows. Let's try another question. Now here we have 3 statements. All boys are jokers. I draw a smaller circle. I write a B here. All boys, and this is a bigger circle for jokers. All boys are jokers. Some men are boys. So some men are boys, it means there's some intersection between men and a boy. So some men are boys. All jokers are caps. So I'll draw this another bigger circle which says all jokers are caps. Now remember that I am not extended this circle to also incorporate M, because that would be a limiting case. That would be an extreme case. You never take extreme case. If you didn't get, I'll just change the ink color and show you what I'm trying to say here. So for example, I have a boy here, and then I had all boys are jokers, then I had few men are boys, and all jokers are caps. Now I could also have drawn a circle like this which takes care which of men also, but this is would be an extreme case that all men are also capped. It is not important that all men would be caps. So you'll this diagram is incorrect and this diagram is not correct, because you always take the limiting case. Limiting case or the middle case. This is an extreme case. Some caps are boys. This is the conclusion one. So some caps are boys. Yes, it's true, because boys lies within this cap. So everything which is in this circle is also a cap and a boy. So this conclusion is correct. Some men are caps. Obviously, all the caps which are in this area are also men, so some men are also caps. Even if you drew the cap circle something like this, I'll change the ink color again to show more clarity. Let's say green. So you drew the cap circle something like this and not the other one, like just touching the joker circle cap. Even then some men would be caps, because everything that lies here is men as well as caps. So don't get confused. All boys are caps. Now this is true because the boy is a smaller circle in this bigger circle of jokers, and caps is even bigger than jokers and it takes care of all the jokers. So all boys are caps is also true. Some boys are not caps. This is false. Generally also, because we cannot draw a negative conclusion from a positive statement. So what are the correct options here? 1, 2 and 3 are the right conclusions. Let's try another question. All A are B. So I have a A here. Then if all A are B, I'll have this second circle here which says all A are B. Some B are C. So I'll draw the circle like this. I will not overlap C with A because I don't know the relation between A and C. So I'll assume that there is no relation. So some B are C. This proves that here, whatever lies here, some B are C. All C are W. I'll draw a bigger circle mentioning W. Now why is this diagram for W wrong? Because I've just made a slight intersection with A and I do not know the relation between W and A. I do not know. So I cannot say that they intersect. So I'll draw this entire diagram again. I have A here. I have B. Then I have C here. And then I have a W here. No intersection between W and A. So this is incorrect only because of this. And no W is V. So I draw a straight line here which shows no relation, and no W is V. Let's look at the first conclusion. Some B are A. Since all A are B, obviously some B are A. So this is correct. All B are A? Definitely not, because A lies in between B and there are so many B's here in this outer circle which are not inside A. So all B are A is incorrect. Some W are C. Obviously if all C are W, then some W are C. This is again right, because everything which lies here is W as well as C. All V are A. Now this we cannot say again, because even if you draw V somewhere here, let's say I'll change the ink color. If you draw V here, like you draw this line, because you mentioned that no V is W is V. If you draw V here, You cannot say that there is an intersection. Only if you draw something like this can you say that all V are W. Not even this. If you draw something like this inside this, it's a very limiting case. So my point is that you cannot go so deep until and unless you are sure about something. You cannot mention this. This will show that all A are V, and this inner circle will show that all V are A. So this is also incorrect. See, the only conclusion that follow are 1 and 3. Let's look at another question. No fool is a great thinker. So I have a fool here, and then I have a great thinker, and there is no relation between them. Some wise men are great thinkers. So I have some wise men here, and they intersect with great thinkers. Some boys are wise men. So I'll have some boys here, and I have made an intersection with wise men. Now remember, I have not made any intersection with great thinkers because I do not know the relationship between great thinkers and boys. So I will not make an intersection. Some boys are fools. So again, I will draw something like this, and this shows that some boys are fools. Again, I have not shown any intersection between wise men and fools because I do not know the relation. Until and unless you know a relation, do not make an overlapping circle. Conclusion: some fools are wise men. I cannot say this for sure. They may be, they may not be. All boys are great thinkers. This is also incorrect. As shown from this, I do not know the relationship between boys and great thinkers. Some great thinkers are wise men. This is correct because I have this intersection which shows me that great thinkers are wise men. No great thinker is a fool. This is also correct because there is no overlap between great thinkers and fools. And also, this no fool is a great thinker is nothing but no P is Q, which also means that no Q is P. So the only conclusions that follow are 3 and 4. So let's look at this another question here. Some dogs are horses. So I draw a circle here for dogs, and some of them are horses. So I draw another circle here which represents horses. No horse is black. Now either I can draw no horses is a black here like this, or I can draw somewhere here no horses is black. But here I need to see in the question if any information is mentioned between dogs and black. Yes, it's mentioned some dogs are black. So this is incorrect and this is the right diagram. So let me redraw. I have dogs here and I have horses here. This is horses, this is dogs. No horse is black. I will draw towards this side because I'm given that some dogs are black. So black has to intersect with dogs. So I have black here, and then I have all dogs are animals. So I draw a bigger circle which takes care of dogs, and I have this animal circle. The conclusion: all animals are horses. This is incorrect because I have some animals here, let's say here or here, which are not horses. No animal is a dog. This is absolutely incorrect because all dogs are animals. So it cannot be possible that no animal is a dog. Some blacks are horses. This is also incorrect because it's mentioned no horse is a black, and here also there is no connection between a black and a horse. And some animals are black. Yes, this is true because I have this here, this space here, which tells me that some animals are black. So the only correct conclusion is the conclusion number 4. Let's move on to the last question for the day. Some trees are houses. So let me draw a tree here. I'll use another color for houses. So, and I have houses here. Banana is a tree. It means that banana lies inside this tree. So this is banana. Now I have not made any intersection with houses here. Why? Because in these statements there is no relation between bananas and houses given. So I cannot assume one. all houses are beautiful. So let me draw a beautiful house with a green color. So this is for beautiful. Now this is, there is no intersection here, keep in mind, because again beautiful and banana, I am not given any relationship between them. It's just that I made the diagram slightly incorrect. Villa is a house, so villa is somewhere inside houses, so this is villa. Now I've drawn no intersection between trees and a villa because I am not given any relation. Let's look at the conclusions. No house is a villa. This is incorrect because I have all these houses here which are villas inside the villa circle. Banana is a house. I cannot say that because as it is clearly depicting here, banana and house are two separate circles. Banana is beautiful. Again, I cannot say that because as I told you, there is no intersection here. There is no relationship between banana and beautiful. All that is mentioned is that all houses are beautiful. The fourth one, villa is beautiful. This is correct. Why? Because villa lies inside houses and houses lie inside beautiful. So villa is beautiful. The only correct conclusion here is the fourth conclusion. That is all on syllogism. So I hope you enjoyed the lecture. Thank you for watching.